So good afternoon, everybody. Welcome to the GeoBridge seminar, and welcome as well to the people who are on Zoom viewing this event remotely. It's my pleasure to welcome Sonke Maus from Norway University of Science and Technology in Trondheim. I shall briefly introduce the speaker. So he studied in Germany, in Hamburg, where he received his diploma, and then he did his PhD in Norway in Geophysical Institute, and he received his PhD in 2007. He then embarked on a career in Norway, first at University of Bergen. Then for a few years, he went freelance and had his own company, CI's Consulting Maus, and then he went back to academic research at the NTNU in Trondheim, where he's currently a senior researcher. Most of his career was devoted to the study of snow and ice by X-ray microtomography, and that's what he's going to talk to us about today. The title of the talk is X-ray microtomography of Arctic ice cores from the MOSAiC expedition. Can synchrotron-based imaging improve climate modeling? Thank you very much.
Thank you. Yes, this one I have to. Is it on? Can you hear me? Yeah, very good. Thank you very much for inviting me for this talk. I'm very happy to talk about the connection between the possibilities that we have here at the synchrotron and climate modeling. And yeah, you may know I will not be able to answer this question in this talk. Can synchrotron-based imaging improve climate modeling? It's more a proposal to try it in the future. Yes, as you know, sea ice on Earth, you see here on the right-hand side, the sea ice in the southern ocean, while in the mid, which is a bit brighter, this is Antarctica. And in the Northern Ocean, you have Greenland, and above you have the sea ice cover. Here it looks that sea ice in the Southern Ocean is the cover is much larger, but it's actually just 20% larger. So it's a bit, what you see on the left-hand side is the summer sea ice cover. And here I think you see the winter sea ice cover in the Southern Ocean. One thing, so we will be concerned with the Arctic now, with Arctic sea ice. And what most of you have heard about is that the Arctic sea ice cover is decreasing. And it's decreasing now since the 80s of the last century. And especially it has been decreasing during summer. I switched back. Yeah. Also September is normally the minimum sea ice extent in the Arctic. March is about the maximum. And you see the winter extent has decreased, but especially the summer extent has decreased. And here you can compare the two extents. September 2007, it was here. It was the second lowest ever that we know from observations. And this is in 1982 here. So it typically prior to the decrease. And we want to understand, of course, how is this progressing? Yeah. Will sea ice disappear from the Arctic, at least summer sea ice? You see winter sea ice has decreased, but it's still a lot there. So this is an important question in climate research. What we also know from the Arctic is something that is called Arctic amplification. And I don't know, yeah. So the Arctic has warmed since 1980. And this warming is 2 to 3 times faster than the global mean. You see here, here, oh, it jumps back image, you see the change in the temperature anomaly in the Arctic. And this is based on different data sets. Yeah. And the gray curve here, this is the global mean. You see Arctic amplification is quite strong. And here you also see the temperature trend, the maps for the Northern Hemisphere. And this is then called the local amplification of the above the global mean. So there are some areas where it's very strong. And yeah, it's clear the Arctic is warming much faster than the rest of the world. And we try to understand in climate science, why is this the case? And I just will briefly introduce three mechanisms. One is the atmosphere. Of course, this is in the atmosphere, one in the ocean, and the third, the sea ice itself. For the atmosphere, we know that during warmer periods in the Arctic, we get a less stable polar vortex. And this means that we get waves and cold air outbreaks that we feel here then in Europe as colder winters, and also, of course, in Northern America. And that's a situation that is connected to the warmer Arctic at the moment. And this, of course, brings also warm air into the Arctic. And it is part of that it strengthens the warming in the Arctic, but it's not all. Yeah. And on the other hand, it's not completely clear today if what comes first. Yeah, does the warmer Arctic comes first, or does this system become unstable and then warms the Arctic? Yeah. This is at least one thing that happens, but it cannot explain all the warming that we observe in the Arctic. The second thing is, what are the ocean currents doing? And there are some recent very interesting observations. And one is, that's just from last year, that it's almost proven with 99% that the Gulf Stream has decreased by 4% over the past 4 decades. So the Gulf Stream, you know, it warms Western Europe. It warms Western Europe. It goes here, and some part recirculates. And so the Gulf Stream has decreased. And a consequence of this is that this North Atlantic here, it has become colder. And here in the Gulf Stream area, it has become warmer. But there's also a part of this Gulf Stream that is passing into the Arctic Mediterranean, how you may call it, the Arctic Ocean, and here Norwegian Sea, Greenland Sea, Barents Sea. And this part actually has not become weaker. We know this from observations during that also are now we have 50 years of good observations. And it's indeed, this is from a paper of Rossby and colleagues, and they show that this branch here, which is going in to the Arctic Ocean, it has actually not changed in mass transport, but it has become warmer, and therefore there is more heat transported into the Arctic Mediterranean. So it may contribute to melting of the sea ice. And maybe for those who are interested a bit more in this, what one thinks is the main cause for the decrease of the Gulf Stream is that deep convection that goes in opposite direction at the bottom, that creates a deep current that drives the Gulf Stream in part. Yeah, it has decreased in the Labrador Sea. On the other hand, we know from observations that the deep convection in the Arctic Mediterranean, it has stayed stable over the past 100 years about. Yeah, so this explains a bit the part of the Gulf Stream that is driven in here into the northern seas. It's set by the outflow over the Greenland, Shetland, Iceland channel here of deep waters. And these deep waters are produced by cooling, also by brine rejection from sea ice, but mostly probably by cooling of the water that is going in here. So in this connection, one can see there is indeed an additional heat transport that could melt some sea ice, and that could raise the temperature in this area. So if you want to put this into the frame of the whole deep circulation and global circulation, then we are looking, of course, into this area. Here is deep convection. Here's water pumped down, and then you get this band of global circulation with deep waters going here, replenished by outflow from the Antarctic. And we get this global circulation, and this takes about 100, 200 years, one circle in this conveyor. And this also indicates, maybe we still don't observe changes here because this is going so slow. The deep oceans, these are large water masses. So this is somehow to see it in the big picture. What we're looking at, sea ice changes in the Arctic, it's important for global climate. But now we are going back. So ocean and atmosphere may both contribute to the Arctic amplification, but the largest effect is actually when there is less sea ice, the solar radiation is absorbed by the ocean, and the Arctic becomes warmer. And this effect is very strong. And that's something that is at least responsible for I would say 50%, the people say perhaps even more, of this Arctic amplification. The question is, of course, how does this continue? Does sea ice cover stay stable during summer, or will it disappear? So now I want to tell about the sea ice, that you better understand what we try to observe here at the synchrotron. At the beamline, at the new BM18 beamline, where we can scan large sea ice samples, which was not possible before. 10 centimeter diameter is our target. Sea ice, this is the typical change of the drifting pattern. This is the transpolar drift current. Sea ice is not simply static, it's drifting all the time. And it's drifting here. You see here is Scandinavia, Greenland, Siberia. And the sea ice is drifting out of the Arctic Ocean. And here are the numbers. That's the year, approximately the age of the ice while driving outside. But it needs to leave the Arctic Ocean. And on this side, these are the observations from the mid of the past century. It's shown years how thick the ice grows. So it's growing during a season, and then it's melting during summer, and so on and so on. And in the end, you see it reaches a thickness between 3 to 5 meters. It was past century before it leaves. And of course, a lot is happening with this ice. It warms during summer to temperatures close to 0 degree, its melting point. And during winter, it then can be as cold as -25. But as I said, this is the situation of the past century. Now, these days, the ice is much younger. It's thinner, what we know, and therefore, a lot of this ice melts during the summer completely and leaves the open ocean. And what we see here for the past 40 years is before about half of the year of the sea ice was older than 1 year in this Arctic Ocean. You see that the colors, red is +5 years. This is in 1985. This is in 2018. So a lot of the ice cover was old, but now the ice has been thinning and thinning. And today, almost no ice becomes older than 3 to 4 years. The ice is either just 1 year old or 2 years when it leaves, and also in the Arctic Ocean proper. So this is the change. And of course, all models that have been constructed during the past centuries, they are somehow validated and calibrated for the thicker ice. But now the ice is just half as thick, and this also forces us to improve the models. And many models have problems with thin ice. It's drifting too fast in the models. So there are apparently things that are not completely understood on the large scale also. Continuing from here, I would now come to the MOSAiC expedition. And this was the clue of the MOSAiC expedition. One of the targets, one of the goals was to follow an ice flow over the course of the whole year and see how it changes, how it interacts with the ocean, with the atmosphere, and make observations every week. And not only the physical properties of ice, but also the biogeochemistry. You may imagine that the ice cover is very porous, and especially when you deform it, you get rubble of ice. And in this rubble, there is a lot of life happening. It's an ecosystem, a very special ecosystem of the Arctic. And what I show you here now on the left-hand side is the drift of the MOSAiC ice flow. Here at this position, the icebreaker Polarstern was frozen in, and then it drifted during approximately 1 year out of here. There was some breaks due to COVID, so the boat had to leave the flow and get new people, new scientists, and go back. But approximately this lasted, you see, it lasted less than a year. And this can be compared with the Nansen expedition. Nansen did actually the same 125 approximately years ago. He was going with the ship Fram to Siberia, and then this ship was frozen into the ice about here in this position, north of Siberia. And then it drifted. The Nansen drift actually took 3 years compared to the MOSAiC drift. But you see, compared to the Nansen drift, the MOSAiC approximately started, yeah, we have here 120, 85. It started somewhere here, yeah. So the MOSAiC drift was not that long as the Nansen drift. But anyway, it was much faster. Yeah, it was almost a factor of 2 faster because what we think, the ice is thinner now and it's drifting faster. So Nansen was actually the first to observe all these ice features, and he proved that the Arctic Ocean is over 4,000 meters deep at certain places, and this is and he was able to take water samples from the depth of this ocean and so on. So this was really crazy what Nansen did 125 years ago. Of course, today we have completely other options to make measurements in the atmosphere, in the ocean below, and also in the ice. And I think the next image shows a bit. Oh yeah, here's some 2 nice images showing the work from there. So here Nansen was reading temperatures from the deep ocean. Yeah. These are thermometers that are sent to depth, and then you draw on a line, and then they shift direction, and then the temperature is frozen there, and shows you the temperature at the depth of the ocean. And here on this side, you see some, I don't know, do you know somebody of the people, Martin, Evgeny? Yeah, at least it's a scientist from the Polarstern, which you see in the background, who are taking an ice core during MOSAiC. So that's a bit of an impression how the work was gone. And what you see here, I would like also to point out is here the ice looks quite flat, but that's probably at this position was chosen for taking ice cores. But here at Nansen's drift, you see there are a lot of ice ridges. They can be 15 meters in total, maybe 3 meters above the water level, 5 meters below. And they are everywhere. And they are also growing around the MOSAiC ice flow. So this deformed and ridged, we call it ridged ice, it's also important for the budget of the Arctic Ocean sea ice. So sea ice properties. Just a short overview. The properties depend, of course, on ice thickness. Yeah, thicker ice is stronger, for example, and they depend on ice salinity because the sea ice is freezing from seawater and it contains a lot of salt. On temperature, they depend on the growth rate that mainly can vary between 1 and 10 centimeters per day in the Arctic. They depend on the growth mode. You can imagine you can have turbulence in the water and then you get a kind of frazzle, grease ice forming. You can have snow cover that slows down the ice grows and interacts with the ice. And then they depend on the vertical gradients of all this. And then, of course, they depend on the microstructure that develops due to growth velocity, ice salinity, diffusion and convection processes. Yeah? And many properties are then important for climate. For example, the optical properties of the ice determine its albedo. Thermal properties determine growth and melt. Fluid permeability determines somehow both, because fluid melt points on the ice can drain off. Yeah. Mechanical properties determine mostly how the ice can deform and pile up. So, yeah, I don't want to talk too much about this image. It simply shows all the processes that will be important when we do try to understand the ice system. Yeah. The microstructure is important for the snow, of course, but it's also important for the ice, because inside the ice you have brine, you have air inclusions, and you have fluxes of salt while the sea ice is freezing that drain out and can make the ocean water quite dense in some areas, even contributing to this global circulation conveyor. And that's also a bit chaotic, but that's real. This is how MOSAiC was set up. Here you see Polarstern. This is the icebreaker. And this is here the ice flow around. And in all these areas, you see the different properties that have been measured. Here was for the first year optics. There were several patches. Then, of course, you have MET-CITY, which means meteorological observations were done there. ROV, where you were sending some robots below the ice. Ocean City, where most of the ocean measurements were done. Albedo, and here's some ridges that were that formed during MOSAiC and which were investigated. Seismics, and so on. So a lot of measurements were done, and this was not always possible, because you can imagine the drift started about here, and then it went into the dark polar night. And during this time, you can't see anything, if not you bring your own light, and the weather can be horrible, and it's very difficult to make measurements then. But anyway, time series over the whole year were performed, and data was collected, and ice cores were collected. So just to give you one motivation why we need all these properties, this sea ice melt pond albedo feedback. It's not simply the albedo feedback when you remove the ice and have the open ocean. It's the albedo feedback that you get when the snow on the ice melts. And then you get large coverage of melt point fraction in the Arctic Ocean. And of course, these melt ponds have a much lower albedo, and they absorb heat. Yeah, and one can very simply thinking, one can say, okay, if the melt ponds drain through the ice, if they disappear, then you expose the ice surface with high albedo again. Yeah, and if the ice is not permeable, the melt ponds will stay there, and you expose the warm water, and it's melting. So, and here what you see is measurements of the albedo of this system. It's not from the MOSAiC expedition, it's from another one. And you see measurements are quite scattered. So it would be really good to have better models here to understand, to model the system. When do the melt points drain? How is the albedo specifically related to the microstructure of the ice? So this is one motivation to understand these ice better. I will come with some more motivations later. And this is just a short overview, sea ice texture and microstructure that we know how it looks like. Yeah, this is 2 meters of ice, and it starts normally growing from the top with a kind of granular ice, because in the beginning the water is somehow turbulent, and you get granular aqueous crystals, typically in the upper 5 to 10, can also be 20 centimeters sometimes. And then you get a transition, and then the ice becomes columnar. Yeah. The C-axis orientation of this ice, it's horizontal, and the ice crystals are columnar and very long. And also the grain size, when you look horizontally, it increases with depth. And in between, in the system, you have brine channels where salt is collected and draining out of the system. I will come to this a bit later, but this is at least how sea ice is growing and our understanding of this ice, yeah, from bottom to top. Of course, when the ice just gets 1 meter thick, it's in principle the same, just that the grain sizes often don't get that large. Here, a shorter look. This is a thin section, a horizontal thin section. This is 1 centimeter, how these ice crystals look like. So it's a kind of lamellar structure. And this lamellar ice structure formation, it's related to actually to a double diffusive process at the interface. The salt is diffusing much less, much slower than the temperature, than heat, I mean. And therefore, you get a constitutionally supercooled region, and you get these cellular ice growth. Yeah. So this is a classical thin section under polarized light. And here's a tomography slice. And this is actually ice that was centrifuged. Yeah. So I have centrifuged the brine out of this ice, and therefore what you see here in dark is now air. But I couldn't get all ice brine out, all salt out, and you see then here the bright. This is liquid brine. This is an absorption tomography slice, and yeah, you see the liquid brine inclusions. They are quite thin, so it's difficult to see this. And I should also say this image was taken at -25 degrees or -20, somewhere in this region. And then you see the brine very brightly. It absorbs much more than the ice. But if you want to go to in situ temperature of the sea ice, especially during summer, then the brine salinity is low. It's just that of seawater. Here it's 10 times almost of the seawater salinity. And then it absorbs very little, and you really need phase contrast to see these brine pattern. Yeah, a closer look to the ice interface. So as I said, it's growing in such a lamellar system. And this is here also an image looking on top. So this is the bottom. It's turned around of such ice. You see these features. They have different orientation. They are, yeah. So this is taken from the bottom of ice. It also has been centrifuged and was scanned at the normal CT. And what you see here is also this skeletal layer, you call it, because it really shows you the skeleton of sea ice when growing at the ice interface. Yeah. It's just to give you an impression that the interface of sea ice is quite interesting. And of course, in this system, a lot of convection happens. The salt has to be driven out from the ice, and also some biological activity happens in there. So if you go to the next scale, then how does the salt brine leave the ice? This is actually happening in a way, in principle, as shown here. You have these crystals, these lamellar crystals, and between them, larger brine channels form. Yeah? In metallurgy, it's called macrosegregation. They draw the brine from the brine layers, and then you form a system where actually in normal sea ice, the circulation is like this. It's down here and up through this system. And when these brine layers become impermeable, the ice would normally stop to lose more salt. Yeah. These here alone, they may not, they may also convect, but when they have been convecting several times, each time such a brine channel convects, the brine is very saline high in, is replaced by seawater, which freezes again partially until the original brine concentration is reached, and so it thins until it becomes stable. So in this way, sea ice is losing its salt, but it also develops a very interesting kind of dual porosity system, yeah, with the thick channels and the crystals with the layers between. And if we really want to understand the system, we have to take large samples. Here, 1 centimeter, this is at least what I show here. Yeah, now these crystals are larger, they can be 2-3 centimeters. So we need to be above a certain sample size to understand these convection systems. Yeah, this is actually a video that I was able to take last year at Tomcat with phase tomography, and it's not sea ice growing, but it's a droplet growth of saline water on an alumina plate. And we were doing this with different directions. This was more or less half vertical direction. This here is ice growing on a horizontal plate. So here's the alumina plate, here's the first droplet, and now the ice continues growing. And I show you the video, and you see the crystals are developing there, and you see the brine between them. This is only possible with phase contrast tomography. So this is about 10 minutes here running. What you also see during this video, I will show it when it's finished, is that you get these concentrations. So the light is brine here. It's absorbing stronger, and the dark are the ice crystals. And you see here parallel pattern, and if somebody would look at this, a sea ice scientist would say, okay, this is sea ice, yeah, but it's actually this droplet ice. The difference is that these lamella here, they are about a factor of 3 to 4 smaller than you have them in sea ice. And this is related to the faster growth velocity. Yeah? So this lamella thickness relates to growth velocity. And what you also get in sea ice is then, you see it here, this macro segregation. While the pores are freezing, some brine is expelled, and this reaches some preferential directions and pattern, and then it's collected there. And in the end, you will get, in sea ice, you will get the larger brine channels, they would be here. And then this will start convecting after a while. Here, the sample is too small. I don't think you need to reach a certain size due to the Rayleigh number that has to be exceeded, and then the sample will convect. It didn't happen here. You also see in this sample there are air bubbles growing. Yeah. And these were sometimes growing, sometimes disappearing again. I can show this image maybe. Oops. I just show the video one. Yeah. You see there are some ring artifacts, but otherwise it's a very good quality of saline ice growth. So in this particular project, we were also interested in the question why sea ice has such low, or saline ice has such low adhesion on the alumina plates or on chips also, that we measured in the lab. And you see a lot of this brine is pushed to the interface, yeah, to the interface of the alumina plate and the droplets that are growing. In the real sea ice world, this brine would be pushed out into the ocean. Yes, so one challenge is, of course, the ice-brine contrast is very low. Here I show it as gray values in absorption. I think this is a normal CT image from an X-ray tube at the lab. And yeah, the difference between ice and brine is quite small. You see it also here in the histogram. So this is extremely difficult, if not impossible, to segment. And so therefore, we need this phase contrast, which was in the video I showed you before. This is phase contrast. Anyway, one can do the sea ice brine segmentation. Here's again this type of sea ice samples that I showed you before. They are centrifuged And depending on the size of the brine channels, I was able to centrifuge a lot brine out or very little. So here you see a lot of air inclusions or channels. This is interconnected, the whole system here. I was able to centrifuge most of it out, and there's some entrapped brine. So the brine is green after segmentation. The air, where the brine has been centrifuged out, is blue, and the ice is gray. And in this ice sample, which was at much lower temperature, it was not possible to centrifuge out a lot of brine because it was already disconnected. Yeah, and then if one then is imaging this at low temperature, the contrast is high enough to see these patterns. Yeah, but if we image at low temperature, we don't get the in situ properties of the ice, and that's what we want to do, and therefore it's so important to get this phase contrast. Yeah, I was already talking about this challenge with the sample size. Here are, what I did. Yeah, I think it's fine. Here are 3 samples of about centimeter size of sea ice, and we say there's a lot of. Here are 2 larger drainage channels, but of course it's difficult to do any statistics or even hydrodynamic modeling with such a sample. Yeah. And also these were imaged at very low temperatures. And then you see the brine in absorption mode here as these layers. You see also here the ice is different. So this is more granular ice from the surface, yeah, where the lamella pattern is lacking. And here you have the lamella. And here you have both, but here you get larger brine drainage channels forming. Yeah, here a bit to show you this motivation. Now, these are the same, that they have the same scale here, 10 millimeter, like here 10 millimeter. So these were the samples that showed you before. This is a sea ice sample that was again centrifuged and then scanned with a normal CT. And yeah, it's just to show that we need a certain size to really describe this system in terms of its hydrodynamics, yeah? Because the distance between these is a couple of centimeters between these main drainage areas. Yes. I can also show you one more result. So this conductivity is in itself a very interesting percolation problem. And yeah, this is here now a 3D. These are centrifuged ice samples, and the red are the pores that were centrifuged out. The yellow is the brine that is disconnected. And here I only have these pores that were centrifuged out to show you how they connect over a very short distance. It's about, in this sample, in the top of the sample, they were not connected, and here they become connected. This is a horizontal section now. And it's very beautiful to look how these, yeah, it's a percolation system, and it depends then really on the dimension of the system when you get a percolation threshold here. So now you see they are disconnected in the horizontal plane, and now they connect. Yeah, and there's a kind of threshold thickness of these ice bridges. The ice bridges in white when the system becomes impermeable. So this can, of course, then be studied, and you can predict permeability depending on the porosity of the ice. Yeah, so this was these hydrodynamic aspects. I have another point that is important to study, and this is, of course, the fracture of sea ice. These are sketches. These are small maps of the Arctic Ocean. Yeah. Here's Greenland, Siberia, Alaska. And the red stuff that you see here, these are based on satellite images. These are crack openings, yeah, in the system. So these are very long cracks, and such a crack here is opening with approximately with the velocity of sound. Yeah. So it's a fracture process. When you have enough forces, then such a crack just propagates through the whole system. And here it's on a, oh, no, sorry. This is, of course, a different length scale here, no 200 meters. You see a bit how these cracks can look like in a young, in a relatively shallow ice area system. But here there are also ridges running where the ice is higher above. And so to better understand this, we also need better information on the small scale properties of this ice. And here we have done some micro CT scanning also. This is now just 8 centimeters here. And this is a CT image of a, obtained at the position where such a crack was forming in the ice. So the crack is really running here over several tens of meters, and then it stops. And at the place where this crack stopped, this ice core was taking, and then I was imaging it. And you see here, this is in 3D how this crack looks like, and one can compute at least estimate the energy, the surface energy of this crack, and also a bit the population of the pattern around the crack, because you get normally in such a system a kind of process zone where the fracture takes place and where the pressure creeps and where the ice gets deformed until it suddenly splits. So understanding or getting better microstructure data would also help us to understand what do we need to know, the fracture energy to split an ice flow, for example. What we need to know to better model the large scales. Yeah, and last but not least, this has only been done for snow up to now. It's if we have a sea ice with very good resolution, we could do some photon ray tracing to estimate the albedo of this. And so this has been done for snow here. These are the snow samples. And then, yeah, you're sending the photon rays through, and you can get estimates of the albedo. And I think this is also there is a potential to get at least better albedo evaluation. Everything we have for the albedo today is rather empirical instead of real models. Yes, now to come back to the sea ice cover is again the question, when will this ice disappear? So what you can, for example, say here, if you look at this time series, yeah, okay, the ice cover is becoming less, but maybe could be that it reaches a new plateau here, a new stable system where it may stay in the future. We don't know this. We don't just know for too little about the structure of the ice to make good prediction of its physical properties. Yeah, and I hope that these cores that we will scan here at BM18 will help into this direction I have sketched. And then, of course, it may be easier to answer questions like this. What I show you here is predictions, quite recent predictions of ice-free Arctic prediction scenarios. And the curves look very similar, but there are big differences. So these scenarios here, yeah, they describe how human beings will continue with emissions on Earth. So this SSP1 to 2.6, it means actually maximum warming of 2.1 to 3.5. This is not in the Arctic, that's the global mean. Net zero emissions around 2075. There was also another scenario with net zero emissions around 2050, but I left it out because it's unrealistic. But at least in this scenario here, we continue max emissions until 2050, and then start to reduce moderately as the politicians maybe like to or don't like to. And this is the more or less we continue as usual scenario. And what you see here is unconstrained means you simply use the model output. This is for many climate models, and you see the spread here, and this is the average. And these are constraints with the current ice concentration and ice area. So the models are somehow constrained by the data that we have. Yeah? When you constrain the models by the data, they predict lower ice cover in the Arctic. Here you have the sea ice area. This here is the level 1 million square kilometer, which is considered as almost zero, so ice-free Arctic. And what you see, if we really manage to go down this to reach zero emissions in 2075, there is at least some hope that we can retain the current sea ice cover. But in the other scenarios, sea ice will be gone by the mid of the century. So there is some motivation, not only because if sea ice is gone and if it's not gone, it's not only something that happens in the Arctic, because it interacts with the climate in the whole world, yeah, and we don't know really what happens. So there may even be affecting the Gulf Stream even more, and so this is a bit of the motivation here, why we should understand the sea ice better and why we should not wait with it too long. As a summary, many properties of sea ice are difficult to measure, and micro-CT imaging and yeah, what you may call digital rock physics applied to compute properties offers the new path now for precise property determination. We need phase contrast tomography for imaging at in situ temperatures, and therefore it's important to go to synchrotron facilities. And representative sample sizes to cover several ice grains are at least above 5 centimeters. And this is the power now of the BM18, that we can do scanning of such large samples. Then this question, may climate models be improved by concise models of sea ice properties? This depends, of course, not only on these results, but also on feedbacks of properties and processes in this Arctic ice ocean atmosphere system that we do not fully understand yet. But there's at least, there are very good arguments to say, okay, let's compute the sea ice properties a bit better than we know them now. Let's build models based on the microstructure. Yes, and I think I'm at the end of my presentation. Would like to thank you very much for your attention, and would be happy to answer questions.
Thank you very much, Sonke, for this really extremely interesting presentation. So we shall take questions from the room. I also remind